Okay, very good. Let's go. So we're going to start off the class pretty slowly today, but before we even do that, there's something else I want to do. So I mentioned that we'll have a quiz every other week, so your next quiz will be next week. And this quiz here was a diagnostic, like I told you, so it technically didn't count, but it'll probably be a lot of good information about where you stand and some things that you might have to review. And some of this stuff we'll be reviewing during the class as well. But on the weeks that we don't have a quiz, what I wanted to do was maybe take the first 10, 15, depends on what I'm talking about, minutes of the class, and sort of talk about some other things. So not things that you'll be tested on, but things I think that will make your experience and your performance in this class better if you heed to them. So it's kind of like a little advice / seminar / kind of thing that I'm just going to talk about. Because I found, been teaching for a long time, over 10 years, and I've noticed some troubling trends recently that I kind of want to help mitigate. So I figured I would just actually talk about that. So let's actually just start the first one of these talks by how to be good at math, or how to be good at this class, or how to be good at anything, really. So I'm going to be telling you the principles that you are going to have to follow, that you need to make sure you're following these things, especially if you're struggling in the class. For those of you who you're kind of catching on to the pre-calc thing kind of quickly and it comes mostly naturally to you, you probably won't have to get this pedantic and this specific, but the day is going to come. If you keep improving and you keep reaching for the stars, you'll eventually hit something that you're not naturally good at. And when that day comes, remember what I'm telling you now. It will apply to math, but it will apply to pretty much anything you want to get good at. And I'm going to tell you the secret of how to get good at something. So, maybe you're doing bad in the class, maybe you did bad on this quiz, maybe you might do bad on the next couple quizzes. What do you do? How do you actually go from a point of not being good to being good? Well, the first thing is you need to set a goal, because good doesn't mean the same thing to everybody. Some people, man, I'm just happy to pass, right? While some people, oh, I can't accept any less than an A. So this is going to be somewhat subjective what your goal is, but you need to set a goal, and some goals are better than others. It's very important that the goal is specific, that the goal is timely, and that the goal is measurable. Okay. So, the title of this is actually a bad example for a goal. So you tell me, my goal is to be good at math. It's a horrible goal. You're not going to have a lot of success pursuing that goal. Wasn't specific, wasn't timely, wasn't measurable, right? So you need to decide what to you it means to be good at math. Specifically, I want to be good at math. What does that mean? I want to get at least a B in all my math classes. Now it's specific, right? What does good at math mean? It means nothing. Getting a B means something very specific. Now you have an actual specific target. You need to know that, oh, I need to get more than a grade of 80 on everything that I do for the class, right? That's specific, right? So for you, I want to get an A. Now your target is 90, right? Oh, I just want to pass. Now your target is 60, right? Whatever it is, be specific. Don't just, I just want to be good at math. You're never going to know when you're good at math by that. Be specific what that is. And be timely. So for example, you always need to set a date. You never want to say, I want to be good at something someday. It's never going to happen, right? Set a time. So for example, you want to be good in this class, the time is clear. You need to be good by the time the final comes around. That's a very specific date, right? And of course it needs to be measurable. That kind of goes to specific, but you need to be very measurable. So that would be like, here's an example of a goal. I want to do well in pre-calc. This means I want to get at least a B by the time December 10th or whatever this final date comes around. And that means I need to get at least an 80 on that final. That is a goal. Anything else isn't, okay? Specific, timely, measurable. If you don't have those things, it's not a goal, it's a pipe dream, and chances are it's never going to come true. 2, you need a why. Now, this is very important, this is very powerful. Depending on the goal, or lots of discipline. The problem is discipline is really hard to maintain when you're doing something you don't like. So if you naturally don't like math, which chances are if you don't like math, it's probably because you're not good at it. So if you do this, it'll kind of fix the fact that you don't like math. But discipline is how you force yourself to do something. If you have a why, you never actually have to force yourself to do anything. So you need to think about, why is this goal important to me? Right? Now, here's something that people often mix up. They never actually set a proper why, just like most people don't set proper goals. It needs to be emotional. It needs to be illogical. Why do you want to get a B in math? Well, it's for my degree requirements. I have to pass this class so I can take. Not good enough, right? I want to do well in class so that I can make my parents proud of me. I want to do well in class so I can feel like I can accomplish something. I want to do well in class because it will make me feel this. Here, I'm chasing a feeling. That's what your goal needs to be, right? No judgment, you don't have to tell anyone. So you could be like, I just want to get it so I can show off on people. I like doing that. Whatever the reason is, it doesn't matter what it is. You can keep it to yourself, but it needs to be emotional and it needs to be a very good reason. Because at the end of the day, reason does not guide your choices, your emotions do, right? Your reason sets the target, but your emotions is what gives you the power to get there, right? A lot of us don't do what we know we're supposed to do. We all know we're supposed to eat right and exercise. How many people do that? Because you logically knowing something never makes you do it. Your emotions make you do something. That's the power you're going to use to get that goal. If you don't have that, you're going to be in trouble. When you don't have this, you're never going to push as hard as you could possibly push, right? Because if you might have a goal, but maybe you're very far from your goal. You want to be a B student, but you're an F student. That's going to take a lot of work, a lot of time, a lot of energy. And when everyone's sleeping and your friends are partying and you're at home doing your math homework, you're going to ask yourself, why am I doing this to myself? I'm not getting anything right. I just practiced 20 problems, I got all of them wrong. Why should I keep pushing? When that question comes, either consciously or subconsciously, you need to have a reason. You're going to know, I need to keep pushing so that I can make my parents proud of me, or I can do whatever. That's very important. Other than that, discipline can work if you kind of like something or you're just a naturally disciplined person. But this makes it a lot easier. You have to have some sort of emotional vision for why you want to accomplish that thing. That's going to help you to push harder when everything is just not going well, when you're frustrated, when you're had enough of this, when you just want to give up. This is what's going to push you through, right? Because when you hit those walls, a lot of people retreat. They just say, oh, I'm not good at math, and they walk away. No, when you hit that wall of frustration, your salvation is on the other side of the wall. You need to push harder. What's going to get you to push is not something logical. It's going to be something emotional. Okay, so that's a good thing. The third thing is you need to have a way to objectively assess yourself. Lucky for you, you have me. You won't always have me, right? When I give you a grade, it is going to be an objective assessment. Now, this might be different from your emotional assessment. You might feel like, oh yeah, I got this class under control. I know, I understand math. I understand what's going on. But if I give you a grade that has a low number, you don't understand what's going on. That's going to be emotionally painful, granted, but I'm not going to lie to you. I'm not. I have no reason to, right? So you're not gonna be an A student and I'm going to give you an F just for kicks and giggles. I'm not going to do it, right? I'm going to give you the number that tells you where you are, right? And if you don't have me, you have to have some other thing outside of yourself to judge you, because we lie to ourselves all the time, really. Okay? I don't have a problem. people who have problems say that, right? You have to have some objective way to assess yourself. Now, in a college class, that's your professor. Outside of college classes, that becomes harder to do. You have to somehow come up with this. 4. You need to have a plan to improve if necessary. So, you set a goal. I want to have a B in this class by this date. You're practicing a bunch of quizzes and homeworks. You are nowhere close to a B, right? So you objectively assess yourself. You're like, yeah, I'm pretty far from a B. Now you have to have a plan to improve, right? Which, I don't want to take up too much time today, so I'm not going to go into this, but over the course of the semester, I'll be talking about specific ways, things you can do to improve. But you have to have a plan to improve. Once you assess yourself and realize you're not at the goal, you need to do something to improve. You don't give up, Jhevon's trying to get me to fail and walk away and throw in the towel. No, put a plan into effect right away and make sure it's a good plan. That's going to be important. 5. Persevere. Rinse and repeat. 3 and 4 until goal is achieved. Do not stop before it is achieved. Now, persevering is much easier said than done. Step 2 makes it a lot easier. And that's it. That's how you be good at this class. That's how you get good at anything, really.
Question.
Yes?
What would be an example of a plan to improve?
Practice more. Let me do another thing, and it might start to answer that question a little bit more clearly for you. So this part is going to be important because some people are working really hard, and some people might even have some sort of semblance of this going on, but they fall back for one specific reason. A couple, but this is a big one. In pursuing the above. Specificity is key, and that will hint to you what kind of plan you would come up with, right? Now, what do I mean by specificity is key? In sports circle, there's a phrase called specificity of training. Basically, this means practice the specific thing you want to get better at. That's all it means. And so that is in fact the secret. If you wanted to, you forced me to say it in a phrase. You want to get better at math? Do more math. That's kind of the secret. That's enough for some people, but others will struggle doing more math because they'll get frustrated, they'll never get anything right. So that's why this plan would be necessary. But you want to be very specific. So one of the reasons why I decided to have these little mini talks is because over time, you know, when students don't do well in class and they come to me in my office hours and they'd be concerned and they'd talk to me and they'd be like, I don't understand what's going on. I did bad on the quizzes, I did bad on the tests, but I'm working so hard, I feel like I understand it, blah, 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 blah. And, you know, I have to give the student a bad grade at the end of the day, and it's like, that's not something I like doing, right? You don't want to fail the hard worker. You want to encourage hard work. And a lot of the times, the problem with that student is specificity is missing. Even if they're doing this, if they're not specific enough, chances are it's not going to work if they actually need help. So what do I mean by specificity? So to do an example for this class, the student might come to me and say, oh, I'm doing bad on tests, but I feel like I understand everything. And I'll ask them, you know, how did you prepare for the test, right? I have to figure out where they are so I can come up with a plan with them to see where they need to go. And they'll say things like, oh, I take great notes, I understand what's going on in class, I watch the lectures on YouTube after the class, so I essentially go to every class twice, I do all my homework, I go to the tutoring center, and they'll say all these things that they're doing. And I believe them, right? And it'll take a lot of hours to do this thing. The problem is, they never said the one thing that they were supposed to be doing, right? You want to get better at taking math tests? You have to take math tests. Anything else is not specific enough, right? And this is true across the board. You want to get good at playing the piano? You have to play the piano. You want to get good at playing basketball? You have to play basketball. You want to get good at public speaking? You have to speak in public. And you have to be as specific as possible. So let's say you are going to be in a race a week from now. You're starting to train for that race. The race is a sprint. If you spend that week running marathons, you're not going to do well in the race, right? Now, it's kind of the same thing. They're both kinds of running, but they're very specific kinds of running, right? So you might be doing something and working really hard at that thing that kind of has something to do with what you want to get better at, but it's not the specific thing that you want to get better at, right? So yes, doing homework, important, but doing homework is different from doing a test, right? When you're doing homework, you have the book there. You can take all the time you want. You can ask for help. You can look up solutions. In a test situation, you can't do any of that. It's not specific enough. Doing well on your homework does not, unfortunately, indicate how well you're going to do on a test. So you might be doing all these things that are kind of like the thing you want to get good at, but you're not being specific enough. You want to get better at taking math quizzes? Do math quizzes. Want to get better at taking math tests? Do math tests, right? You can't decide, oh, I want to get better at basketball, and you spend all your time practicing free throws. Yeah, it's important to practice your free throws, don't get me wrong, but basketball is more than free throws, right? You have to learn how to dribble, how to run, how to pass, how to shoot a two-pointer. There's so many specific things that, yes, you're practicing something that has to do with basketball, but if you're not practicing the specific things, if someone throws you into a game, you're not going to do well. So that's important. So when you're coming up with a plan to improve, that's going to be a part of it. So if you realize that, okay, I didn't do so well on the test, you start to assess yourself. What did I do to prepare for that test? Well, I did a bunch of homework. What should my plan to improve be? Well, do more quizzes. How are we going to do quizzes? Well, you're going to take a quiz that I wrote. You're going to go to a tutor. You can get tutoring for free, and you can say, here's a quiz that my professor wrote. Using this format, write a bunch of new problems for me and let me do them under timed conditions. Check my work afterwards and see what's going on. Okay, do that. Okay, your tutor grades you. You got a C. Okay, give me another one. Write a bunch of new problems again. Let me time myself and go through it. How do I do now? C+. Okay, getting better. Do it again, right? At the end of the day, you want to get good at a quiz, you need to practice quizzes. Before the day of a quiz, before the day of a test, you need to have done a bunch of quizzes and a bunch of tests. You need to work out all the kinks before the day of reckoning comes, right? So yeah, it's good to pay attention in class. It's good to do your homework. It's good to do all these things, but it's not specific enough. Your grade in this class comes from very specific places. 1, attendance. So you have to get good at showing up early all the time. 2, homework. You have to get good at doing homework. 3, quizzes. You have to get good at doing quizzes. And 4, tests. You have to get good at doing tests. Now, all these things will have overlaps, but they're all distinct, very specific things. And to get good at any one of them, you have to do the category of that one thing. So if you practice a bunch of quizzes in order to prepare for a test, it's not specific enough. And unfortunately, a lot of that time is going to be wasted. Everything you do must go towards a specific goal. Everything you do, there has to be a very specific reason you're doing it. So I'll give you advice on, oh, you need to create a formula sheet or something like that. What's the point of creating a formula sheet? So you can remember the formulas that you're going to use on a test. If you create a formula sheet but you never remember the formulas to use on a test, you wasted time. And you're going to come to me, oh, I rewrote my notes and I created all these formulas, and I still did bad on the test. And yeah, that was good that you did that, but you never used it for the specific purpose that you were supposed to use it for. Okay? So we'll stop there. 2 weeks from now, I'll do another installment of one of these. But that's kind of the overview. Make sure you go through these steps. Be specific on what your goal is. Make sure you're hitting that goal every time. Make sure you're practicing specifically at what you want to get better at, and persevere, nice children. Do not give up. Now, let's actually get into the lecture. So, I want to start out by talking about some very basic things. So, when does this class actually end? 12:45, right? Yes. So, be warned. In general, when I'm teaching, I like it to be a back and forth conversation between me and the class, but the next 2 or 3 classes is just going to be me just talking to you guys a lot. I'm going to be like dumping a lot of information on you. And the second thing you should be aware of is that it's probably going to be boring, a lot of it, because it's going to be things that you feel like, you know, you're going to be rolling your eyes. Why are you telling me? Oh, no. Pay attention regardless. Okay? Because a lot of the times you don't know things as well as you think you do. It just, not you guys, specific, everyone, this is the case, right? A lot of people just will misestimate their abilities or their knowledge of something. Just because it seems familiar, we're more likely to think we know about it. Oh, I did that in grade 9, I did that in grade 10, and I saw that before. So you'll tend to feel like I don't need to really pay attention now because I already saw this, but pay attention. So that's just what I'm going to mention. So the first few classes, I'm really going to start from the basics, some things that you know about, but it's very important that we're going to start from the foundation and build our way up so everyone's on the same page, and as far as I can tell, no one has any gaps that they're not used to. So we will start with 1.1 of the text, which the focus is the real numbers. So I'm going to tell you about a set of objects called the real numbers. But to build them up, we need to first know about some other kinds of numbers. So let's do that. Here's some definitions. And in future lectures, you guys should, future talks, you guys should remind me about how to read notes. That's also something I think students do incorrectly all the time. So we're going to do some definitions of different numbers. There is a symbol that you will see, and this refers to what is called the natural numbers. Okay. For us, this is going to be the positive whole numbers. 1, 2, 3, 4, dot, dot, dot. Right? So a set of all of those numbers. We call them the natural numbers. One thing I will mention here is that you should notice that some sources define n to include the number 0. Not everyone does this, but some sources do, so you should just be aware. If you're reading a textbook other than our textbook, they might include 0 with the natural numbers. But if they do that, there will be a glossary somewhere in the back or the front of the textbook that tells you how they're thinking of the natural numbers. So just be aware that 0 isn't always included, but we will not include it. I would think of the naturals as the positive numbers. There is also a set of numbers that we call Z. Okay? These are the integers, or the whole numbers in general. And this is the set of the positive naturals and the negative naturals and 0. So it would look like -3, -2, -1, 0, 1, 2, 3. Or some people might write as 0, plus or minus 1, plus or minus 2, etc. So you might have a couple questions at this point. If it stands for the integers, why did they use the number Z? And the second question you might have is, why is Jhevon pronouncing it Z? Well, the answer to the first question is Z actually stands for the German word Zahlen, which is plural for numbers. And the answer to the second one is because that's how it's pronounced. And we should all do our part in setting the record straight. Okay, so we call these the integers or the whole numbers. If I use this kind of symbol, I'm talking about these guys over here. We also have the set called Q. Now Q stands for quotient, and this is the set of all things that look like this. A divided by B, such that A and B are integers and B is not 0. So it's very hard to write down a nice formulaic set for these, but it'll include things like 1/2, -3/4, 57 over 13, etc. Anything that looks like that form, we call, these are called the rational numbers. We also know them as the fractions. So anything that looks like that. We already know we can't divide by 0, so B cannot be 0. But if I take a ratio of two integers, we form what we call a natural number. Now, real numbers is something that we work with every day, but they're actually surprisingly hard to define. There's actually no good way to define it at the level of pre-calc. You actually need some really advanced math to say specifically what a real number is. But for us, the following will be good enough. Right, so the symbol would be boldface R. We call these the real numbers. Not that they're fake numbers, but they're just called numbers. Okay. And how you think of these is something like all possible decimal expansions, all numbers on the number line. You think of it also as Q with the gaps filled in. So it turns out, if you were to plot a number line, and I was to plot all these kinds of things on that number line, so I would have 0 over here, I would have -3 over 2, I'd have 1, I'd have 2, I'd have a half. Like if I were to plot all these points on the number line, it turns out that there are points that you won't be able to actually get. There will be gaps in here. There will be holes in the number line where there is no fraction that you can write down that will actually fit in that specific position. So for example, there might be a gap here between 1 and 2 where the number radical 2 will occur. Now that number cannot be written as a fraction, but it's a number as far as we know. Right, so it's roughly 1.414 blah blah blah, but it can't be written as a fraction, but it's a number that exists. It's a possible thing I can write out as a decimal. Pi will also show up, things like that sort. So these are all numbers that we can't write them as a fraction, but we do think of them as numbers. So there will be gaps left if I plot all the fractions. And the real number comes in when you fill in all the gaps. So you fill in the entire number line, and you make any position on the number line attainable. Once you have that kind of system, we say you have a real number system. Now, that is super important because this is pre-calculus, and for calculus to work, we need to have no gaps. You're going to learn about things like limits, and you need to be able to pretty much attain any position on a number line that you want to in most cases. So the real numbers are very important in the study of calculus for that reason. They fill in all the gaps left out by the fractions. So there'll be all sorts of weird numbers that you can't write them as fractions, but we want to think of them as some kind of quantity, some kind of size measure. We also have what we call the irrational numbers. Often we write this as r minus q. We call these the irrational numbers. Not that they're crazy and irrational, it just means they're not rational. They're not a ratio of two things. So this will be the set of everything on the number line that is not a fraction. So things like pi will be in here, radical 2 will be in here, pi squared over 4 will be in here, e will be in here. I'll talk about that number pretty soon. A lot of things, everything that's not a fraction, we call it an irrational number. We also have c, which is the complex numbers. And this is basically anything that looks like the following: a plus I times b, such that a and b are real numbers, and I is defined to be the square root of -1. And as I mentioned, we will not be discussing complex numbers in this class. So, not important for this class. So if you're solving a problem where a complex number is the answer, as far as I'm concerned, you should write no solution. But it is a very important kind of number class. But at a higher level math class, we'll start to talk about these guys. But knowing about all the other numbers and their properties is going to be important. So those are the sets of numbers that I expect you guys to actually know about. Okay, what's next? Okay, let's talk about the properties of real numbers. So again, these are the things that many of us, including myself, would kind of intuitively know about. And so I'm literally going to read off some of them to make sure that I don't even skip something because I just don't remember to mention it. So different things like, there are things called the commutative property. And properties. There's one for addition and multiplication. So this says a plus b is equal to b plus a, where a and b are real numbers. How many symbols do I actually need here? C. So let a, b, c be real numbers. Then a plus b is thought of as the same thing as b plus a, and a times b is thought of as the same thing as b times a. This is called commutativity. It means that the order does not matter. When it comes to addition and multiplication, order does not matter. There are the associative properties. And that is to say that when you have a list of products or sums, positive sums, the order of the parentheses will matter. So this means that if I have a plus b plus c, a plus b plus c, I can add a and b and then add c, or I can add b and c and then add a, and the result will be the same. Similarly, ABC, ABC, I can multiply these two first and then multiply the third, or I can multiply the second two first and then multiply by the first. And those will always give the same result if a, b, and c are real numbers. These will always be true. There are also things called the distributive properties. And this says that a times b plus c, this is how multiplication and addition play together, is a times c, and get b plus c times a plus b plus c. So these are the distributive properties. Now, here's a note which, it's not something I'm going to test you on, but knowing this fact will make certain things psychologically easier and will kind of give you like a cheat code to this whole math thing, actually. So, here's something that a lot of people find strange the first time they hear it. The above are axioms. Now, what an axiom is, it's a mathematical fact. Accepted on faith. These are things that we pretend to be true, that we have no idea of really knowing whether they're true or not. These are just the rules of the game. It's sort of like when you kind of think about chess, there are certain rules of the game. The knight moves this way, the bishop moves that way, the queen moves this way. Someone came up with a game and just invented certain rules. And there was no reason for them to make those rules. Well, there might be some sort of thing that they wanted to talk about those rules. But at the end of the day, the rules are essentially arbitrary. Now that is very important psychologically. Why? Some people kind of think like math is this thing that is the ultimate truth of the universe, given to us by the gods, and the gods choose who is good at it and who is bad at it. I'm just not a math person. This is not the case. Math is based on rules that we made up. It's a game. It happens to be a very useful game, but it's just a game. And in the same way that you can get better at chess, you can get better at math, because it's something that's based on a bunch of rules that some dude a long time ago made up. Okay? Or dudes, or dudettes. A bunch of people made up a bunch of rules. This is how things work. Learn the rules and follow the rules, and you're good at math. That's really it. It's not something mystical or mysterious. Okay? And in the same way, you might be able to say, okay, but some people are really good at chess though. But the thing is, you don't have to be a chess grandmaster to consider yourself good at chess, right? You can be really good at chess, but just not the best in the world. For pre-calc, you don't have to be the best in the world. You have to be reasonably good at these rules. And that gives you some hope. At any given time where you're like, I don't understand this, you can kind of retrieve in the safety net of knowing, oh, it's just some rules that are made up. So I might not understand it, but I can definitely just follow the rules. And at the end of the day, that will ease a lot of frustration at the end of the day. Instead of your racking your brain, why is this true? You can remember, it doesn't really matter why it's true. I just know it's true. These are the rules. Okay? And the rules tell you you can improve, you can get better, you can learn to be better at chess, the same way you can learn to be better at math, because both are just based on some arbitrary rules, really. Now, there are reasons why we want to believe these rules. Right? So it's not that someone just randomly made up the rules. They conform to reality as best as we know it. Right? So if you put 3 sheep in a pen and then put 2 sheep in a pen, or you had put 2 sheep in a pen and then 3 sheep in a pen, at the end of the day, you'll have 5 sheep in the pen. It makes sense that this is true. Right? So it's not some random rule I just made up. It kind of makes sense based on just looking around and seeing how the world works. Yeah, something like this is probably true. So we just accept it on faith. This is always true, all the time, no matter what the number is. Right? And you might see, even like things like that look more esoteric, like the distributive law. Why would that be true? There's no proof for the distributive law. But it makes a lot of sense. So, for example, look at the distributive law. Why would it be the case that something like this is true with numbers? Well, consider this idea. Let's say I have a rectangle here, and I slice it. And this length here is A, that length here is B, and this length here is C. Right? Which means this entire length here is A plus B, right? Now, let's say I wanted to find the area of this rectangle. One way is to look at the area of the big rectangle. Which we would define, and that's something that we defined, by the way, the area of a rectangle. Someone just made up the rule. Oh, it's length times width. But following that rule, length times width, we would get A plus B times C, right? Another way that we could do it is we could add the areas of the 2 smaller rectangles. Right? So what's the area of this one? Well, it's A times C. Plus, what's the area of this one? Well, it's B times C. So it makes sense that the C should be able to distribute to each of these, and then we add them separately. It makes sense for these two quantities to always be equal, right? Now I don't know that it's really always equal. Take it on faith. It makes sense. Like I can draw a picture, I can point to it and say, oh, that's true. So all these rules that we're making up, you can even consider them arbitrary. There's no reason why they have to be true. But in a math class, and in math in general, we pretend all these things are true. Everyone's playing according to the same game. And the people who are better at it are the people who know the rules better. The people who know the rules better are the people who practice the rules more. Not that they're gifted or they were chosen by the gods, they just practice the rules more. And they specifically train to be better at practicing the rules. So we have those properties. Also, I want to talk about some terminology here. And yes, I know it's an eye roll. We all know this, Jhevon, but switching from one situation to another, these processes have names. So AB plus HC. Now, if we're moving from a situation like this to a situation like that, that process is called expanding. If we're moving from a situation like this to a situation like that, that process is called what? It's called factoring. So when someone tells you factor this, what they mean is you want to go from a situation where everyone's all spread out to a situation where they're connected by parentheses and multiplication, right? If I say expand, it means you want to do the opposite. Go from a situation where they're all connected by multiplication and parentheses to a situation where everyone's all spread out. And knowing what these mean and knowing when to do them is very important to the rules of the game. There are certain things that you'll always want to do as opposed to the other. Like for example, solving an equation will often involve factoring. So if you want to solve an equation, chances are you're going to want to be doing this. And a lot of times I'll see students try to solve equations by doing this. It's kind of the wrong way to go because they never really see a strategy. Which I'll be talking about strategies later, but that's just what we call this kind of operation. What else do I want to mention? Let's talk about addition and subtraction. Now, originally I was really going back to basics and I was like going to show you on a number line what it means to add two things, but I'm going to take it for granted that you guys kind of know what it means to add two things. I assume everyone knows 2 plus 3 is 5 and so on and so forth. And, 3 minus 5 is minus 2. Like, wait, what? Like, yeah, I'm going to just take that on faith. I think at this point you can kind of skip over something. But I do want to mention some other important things that apply to addition and subtraction. For example, this number, that's not an O, this is a 0. It is a real number, the guy that's in the middle of the number line. We call it the additive identity. That's because if you add it to any other number, it gives you the identity of the number. Right? Because 0 plus A is equal to A, and A plus 0 is equal to A for all real A. Another thing, there is something called the, if A is a real number, there is an expression that we define, we make up, we call it negative A. Is negative A, and it is the additive inverse of A. Now, Here's a word that you would have seen in the math class before. Inverse just means to undo. To actually invert something means to undo it. So this is kind of showing you that the negative can undo a positive, and that's going to be very suggestive of how we'll do things with addition and subtraction. One important thing to note, negative we tend to mean is to the left of 0 on the number line, but negative a does not need to be negative. So let me talk about what I just meant. If a is equal to negative 3, that is a real number, then negative a is going to be equal to positive 3, which is positive. Right? And that means to the right of 0 on the number. So there are students who just have the idea that every time they see a negative, it means it's a negative number, it's on this side. Not true in general, right? That might cause some friction in the future. So negative is a term, it kind of means the opposite of the regular number, but negative, just as a category, means to the left of the number line. And so if you mix that symbol with another number, it doesn't necessarily mean it's on the left. It could be on the right, depending on what the original number was. So, yeah, again, these are things that no one really thinks about, and they think they know it, but they get in trouble because of it. Now, the important property is the following. Is that a plus negative a equals 0. That's what it means to be a negative. And again, eye roll, but it's actually important that you know that that's what it means to be a negative. Find a number that when I add it to this thing, it gives me the additive identity, then that number is called the negative of a. So you want to think of negatives as kind of being the opposite of addition, in the sense that plus sign tells you that you're taking steps to the right of it, and then negative sign means you're taking steps to the left on the number line. And we also will define a notation. A minus b means a plus the negative of b. Now, let's talk about the properties of negatives. I know more things that you think you know already. I just bear with me. Let's do. Minus 1 times a equals negative a. 2. Minus a minus a equals a. 3. Minus a times b equals a times minus b equals minus ab. Those are all the same. 4 minus a times minus b is the same as ab. 5 minus a plus b is equal to minus a minus b. 6 minus a minus b is equal to minus a plus b, which is equal to b minus a. And these, again, they look kind of similar to the properties that I mentioned before. The difference is these are not axioms. These are things you can actually prove. I know a lot of you take for granted that if I multiply something by -1, I get the negative of that thing. But that was something that someone had to figure out at some point. That actually isn't something that's natural. So everything in this list, you might think of it, and it's funny, the things that are made up rules. People think of them as being given to you, and the things that are people think as being given to you are actually legitimate rules that someone had to derive and figure out. These are not axioms. You can actually prove all of these. I'm not going to, but you can. Because this class, we're not going to do a lot of proofs. I mean, I'll do proofs from time to time, but I'm never going to ask you to do a proof on a test or anything like that. So, but if I think it's cool or kind of instructive, I might show you where something comes from. But you're not going to be responsible for proofs in this class. Let's talk about multiplication and division. This section is going to include a lot of people's favorite topic, adding fractions and multiplying fractions and dividing fractions. Everyone loves fractions, right? I love fractions. I'm going to remind you how to add fractions, how to multiply fractions, how to do all that. But we need to talk about division and multiplication. And as I will show with some examples, I'm not sure today, knowing how to do these with numbers, by extension, you'll know how to do it with formulas and random expressions. I'm kind of going to start to generalize slowly here. So knowing these rules, they're very important because at any given day, when you're doing something that looks more complicated, it really isn't. They're always following the same rules in the background. And so that should help you out. One is called the multiplicative identity of real numbers. That's because if you multiply 1 by anything, it gives the identity of the thing. That's because 1 times a equals a, and a times 1 equals a. So that's the first thing. So if a is a real number and a is not the same as 0, then 1 divided by a is also a real number. You can't divide by 0. And the expression 1 over a, we call this the reciprocal of a, or the multiplicative inverse of a. So if I talk about reciprocal, I mean this. I mean put something in a denominator. It's called the multiplicative inverse because, again, they undo each other. If I take a and I multiply by 1 over a, the result is the multiplicative identity. In the same way, a negative is the additive inverse, because if I take a plus a negative a, it gives me the additive identity. And so here's one thing you can talk about: division undoes or undoes multiplication. Sort of in the same way. Subtraction undoes division. Subtraction undoes addition. Right? That idea helps us when it comes to solving equations. If I realize there's a +2 and I don't want it, I can -2 on both sides to get rid of it. Right? So that's where that idea comes from. And we use notation here. We use this symbol to mean a divided by b, or a times 1 over b, or 1 over b times a. These are all exactly the same expressions. They are mathematically equivalent. And of course here we're assuming b is not equal to it. And I'll talk about this idea a little bit more, how you can kind of split a fraction by sliding pieces of it off. As long as what's in the bottom stays in the bottom, you can kind of do this little maneuver, and it actually helps a lot of times. And in A over B, A is called the numerator, which when I'm lazy, I'm just going to write num. And B is called the denominator. And when I'm lazy, I'll call it den. Another way you might refer to B is divisor. And A over B is sometimes called a quotient. Right, that's where the Q comes from in the rationals. Okay. Now again, I'm going through this painstakingly because again, I know it's something that you guys would know already, but I do want to emphasize certain things that how we name things, what I'm saying. Because when I'm going, later in the semester I'm going to be taught, oh, do this to the numerator, do this to the denominator, take the inverse of this, and I want you to be able to understand what I'm saying to you. And so this is actually very important. And just in general, a pro tip, language and how you speak and how you talk about things is important in general for cognition. The more you can talk about something, the better you'll understand it, right? So a lot of times when a student isn't good at math, they won't be able to talk about math very well. So I did bad on this quiz, and I'll just say, okay, tell me what you think about when you're doing this problem. They won't be able to say it, right? So thinking of the words you use, it's very important. There is even there's a podcast, I think you can find it on NPR, and it's called Words. Read that, listen to that podcast. And it kind of tells you how important language is when it comes to learning something and being able to figure out a problem. And you can, and they do experiments where they take away an adult's ability to use language and they literally devolve to the intelligence of a toddler. Like they're very simple things that they just couldn't figure out once they took away language from their brains, and it was amazing. So it's actually, language is very important. So when I'm telling you, oh, this is called this and this is called that, it's very important that you pay attention to that as well. Being able to talk about something is very important, more important than you realize. And it's one of the things that no one thinks about. No one thinks about vocabulary when they're learning math. It's very important, trust me. So I understand a lot of eye rules, but I'm writing this down on the board because it's important. That's not always going to be understood, but just trust me. Everything I write on the board, I write it down because it's important. I don't actually want to waste time up here. Let's look at properties of fractions. So here we're going to talk about multiplying fractions, adding fractions, dividing fractions, LCD. How do you find an LCD? How do you generalize this to things that aren't just numbers? That's what we're going to talk about now, which we will continue. We're not going to be able to do a lot of examples, but maybe I can just tell you the properties. And next time I see you guys, which I think is tomorrow, right?
Yeah.
Monday, Thursday. So tomorrow we'll actually finish this section. We're going to talk about a lot of important stuff that's going to help you with simplifying. And at that point, we'll get into turf that some people just didn't know or didn't know well enough, or they're kind of inefficient. I'll talk about several ways you can do something and what is more efficient in practice and all that kind of stuff. But let's just remind ourselves of the properties here. And these extend naturally to real numbers. Right, so how we define fractions is ratio of integers, but if you pretend A, B, and C are real numbers, the same rules would actually apply. So one, if I take A over B times C over D, what do I get? AC over BD. You multiply across. 2, if I take A over B divided by C over D, what do I get? AD BC, right? Some students refer to this as keep, change, flip. Keep the first one, change this to a multiplication sign, flip the next one, and multiply. And that's AD over BC. Do I want to mention this at this point? It's a good thing to know, and this is going to help you out in the unlikeliest of situations. But to understand that when someone writes this, there are multitudes of ways that that can be expressed. You can write this as A times D over BC. You can write this as 1 over B times AD times 1 over C. You can write this as A times D times 1 over B times 1 over C. There's so many ways you can actually rewrite this fraction. The important thing is to remember that things are in the numerator need to stay in the numerator, right? So once I slide the C off, if I slide the C into a separate fraction on its own, it needs to be a 1 over that C. The C needs to stay in the denominator. If it was in the denominator in the original, it must be in the denominator like all the time. Other than that, when you have multiplying fraction, you can change order and you can slide things around into what's convenient. And there are so many situations in which that's so useful you can't believe. There's so many times where a student will get stuck on a problem. You can explain this to them, oh, now it's super easy. Right? People don't think about that, but that's true, so know that. Okay, more properties. So when it comes to a fraction, you can slide things around when you're dealing with multiplication. Just make sure numerator elements stay in the numerator, denominator elements stay in the denominator. Do I have space here? Third thing. Now, A over C plus B over C is equal to A plus B over C. 4, if I'm adding two separate fractions, A over B plus C over D. Right? Now it turns out when addition is there, that's not the rule. The rule looks slightly more complicated, but it's going to be A times D plus C times B all over B times D. So a lot of students, if you might take, oh, 1/2 plus 1/2, is that 1 plus 1 over 2 plus 2? You will of course realize that the answer is no. Right? I shouldn't put a green there, I should put a red. Right? So when you're adding fractions, you don't just add the tops and add the bottoms. When you're multiplying fractions, you just multiply the tops and multiply the bottoms. It's not true for addition. Here's an example why it won't work. 1/2 plus 1/2 should be 1, but if I just add the tops and add the bottoms, what do I get? I will get 2 over 4, which is actually 1/2, which, yeah, I know that's the wrong answer. So this is how we add fractions, not that. Now I'll kind of explain where that formula comes from a little bit later when we talk about LCD and all that sort of stuff, but for now you can know that that's how we add addition. It also works with subtraction, so plus or minus, you just keep the same sign here. Here's another property. A times C over B times C is A over B. We can do what we call canceling. We can cancel the C. I know that might seem obvious, but there are many contexts in which a move like that would actually be illegal. When you're dealing with real numbers though, that's perfectly legal, and we might refer to this as canceling common factors. So if I talk about canceling common factors, what I mean is this specifically. If A over B equals C over D, then it turns out that A times D will equal to B times C. This is often referred to as cross multiplication or cross multiply. Okay. So if you have two fractions, how can you know that they're equal? By doing a cross multiplication. This statement is true whenever those fractions are the same. So if I have 1/2, how do I know it's equal to 2 over 4? Because if I do 4 times 1, I would get the same number as 2 times 2, right? Here's another thing to note. A fraction can only be 0. This is a very important one too. If the numerator is 0. The denominator can never be 0, and it wouldn't be a fraction. So that's going to save you a lot of time and headache because you'll realize certain things. So for example, you would realize that 1 over x is not equal to 0 for any x. You'll also know that x squared plus 1 over 3 plus x equals 0 has no solution, right? You automatically know things like that right away with no calculation necessary. Because here the numerator is 1. It's never going to be 0. It's always 1. So there's no way that the fraction can be 0. Here, the numerator is going to be 1 or bigger. So the numerator is never going to be 0, so the fraction will never be 0 overall. So you actually, if you see something like this equals 0, don't waste time solving it. It's never going to equal 0. This will never be 0 for any x because of this rule. So there will be a lot of times I had students like going in, try to solve stuff, and then they either get it wrong or they conclude that it had no solution. And I'm like, you should have known that by looking at it. Like, why did you waste all that time? Okay, I think we're done for now. We'll use these rules and a lot more stuff tomorrow. I will see you guys.